Hey everyone, Adam Infinity here, and welcome back to Singularity Today. Today, we're diving into a fascinating collection of research papers that showcase the incredible advancements happening in artificial intelligence. From using AI to detect breast cancer in mammograms, to building robots that can understand social cues and even edit images based on your words and reference pictures, we're about to explore how AI is transforming the world around us. Get ready to be amazed as we unveil the future of AI, one groundbreaking research paper at a time. In the research titled Multi-View and Multi-Scale Alignment for Contrastive Language Image Pre-Training in Mammography, the authors tackle the challenge of applying cutting-edge language, image pre-training, clip to medical imaging, specifically mammography. This is tricky because mammograms have limited labeled data are very high resolution, and the areas of interest are tiny. The research team developed a new technique called MAMA, Multi-View and Multi-Scale Alignment, which takes advantage of the multi-view nature of mammograms, zooms in on the important details, and uses a smart fine-tuning method. MAMA significantly outperforms other methods on two real-world mammography datasets, EMBED and ARSNA Mammo, while using only 52s of the size of the biggest competitor. This research is impactful because it brings advanced AI techniques to mammography, which could lead to better detection of breast cancer and potentially improve patient care. It's like giving AI a magnifying glass and a better understanding of mammograms, making it more effective at analyzing them. This could eventually help radiologists make more accurate diagnoses and improve patient outcomes. In Find Rhinos Without Finding Rhinos, Active Learning with Multimodal Imagery of South African Rhino Habitats, the researchers looked for a way to monitor rhinos without directly observing them. Instead of tracking rhinos themselves, they focused on mapping rhino dung piles called middens, which provide valuable information about where rhinos are active. They developed a system that uses a combination of images, thermal, regular color, and LiDAR, to identify these middens. This system significantly reduces the amount of manual labeling needed to train the models. They found that the location of these middens is not random, but clustered in specific areas. This means rangers can use these maps to direct their anti-poaching efforts to areas with high midden density, increasing the effectiveness of their work. This research could help to protect rhinos and potentially be applied to other endangered species. In the research titled AI-Powered Augmented Reality for Satellite Assembly, Integration, and Test, the researchers explored the use of artificial intelligence and augmented reality to improve the process of building satellites. They developed a system that uses Microsoft HoloLens to guide technicians during assembly, providing them with real-time instructions and feedback. This system uses computer vision to recognize objects and their positions, allowing it to provide accurate guidance. The research found that the AI models used in this system were very accurate, with a detection model exceeding 95 accuracy. This shows that this technology is reliable and can be used in real-world scenarios. The researchers also developed a way to automatically label real data, which greatly sped up the training process for the AI models. The research concludes that this AI-powered augmented reality system can be a valuable tool for automating critical tasks in satellite assembly, leading to more efficient and accurate processes. This technology could have a major impact on the space industry, potentially making satellite assembly faster, cheaper, and more reliable. Imagine technicians wearing augmented reality glasses, that guide them through each step of the assembly process, helping them avoid mistakes and complete their work more efficiently. This could be particularly useful for complex tasks, where even small errors can have major consequences. In addition to satellite assembly, this technology could be used in other areas of the aerospace industry, such as aircraft manufacturing or rocket assembly. It could also have applications in other fields that involve complex assembly processes, such as manufacturing, construction, or even surgery. In the research titled Efficient CrackNet, a lightweight model for crack segmentation, researchers introduce a new model called Efficient CrackNet for identifying and outlining cracks in images, particularly of pavements. This is a tough task because images of cracks can be blurry, have weird shapes, and have lots of distracting background noise. Cracks in infrastructure like roads and bridges are important to find early because they can cause big problems. Existing methods that are simple and fast are not very good at finding cracks in these difficult situations. The efficient CrackNet, however, uses a special combination of different types of machine learning techniques to get better results. It uses a special kind of convolution called depth-wise separable convolutions and a structure called mobile leavitt block to analyze images at different levels of detail. It also uses a way to specifically find the edges of cracks and a way to make the model even better at finding important features in the images. When tested on real datasets, Efficient CrackNet was able to find cracks with much better accuracy than other simple methods, while still being very fast and needing less computing power. The researchers conclude that Efficient CrackNet is an effective and efficient solution for detecting cracks in the real world, leading to better maintenance of infrastructure and improved safety. This could help construction companies quickly identify and fix cracks in roads or bridges before they become dangerous. The research also opens up possibilities for better inspection of other structures like buildings or even airplanes for early detection of cracks. In the research titled DiffSSC Semantic LiDAR Scan Completion, using Denoising Diffusion probabilistic models, the researchers tackle the problem of sparse point clouds generated by LiDAR sensors in autonomous driving. These sparse point clouds can lead to incomplete and inaccurate scene representations, hindering the vehicle's ability to perceive occluded areas. To address this, the researchers propose a new approach called Semantic Scene Completion, SSC, that uses diffusion models to fill in the gaps and provide a more complete picture of the surroundings. They utilize a combination of denoising diffusion processes and semantic LiDAR point clouds to generate a richer and more detailed scene representation. The research concludes that their approach, DiffSSC, outperforms existing methods for SSC, demonstrating its effectiveness in enhancing scene understanding for autonomous driving applications. This research can have a significant impact on improving the safety and reliability of autonomous vehicles by providing more comprehensive and accurate perception capabilities. Potential use cases include enhancing object detection and tracking, improving path planning algorithms, and supporting advanced driver assistance systems. In the research titled GSON, a group-based social navigation framework with large multimodal model, the authors propose a system to help robots navigate social environments in a way that is both safe and considerate of people. The system uses a large multimodal model to understand the social structure of a group of people and then plans a path for the robot that avoids disrupting this structure. Think of it as a robot learning to navigate a crowded street without bumping into anyone or cutting in front of a group of friends. This research could lead to better social interactions between robots and humans allowing for more seamless integration of robots into our daily lives. Imagine robots being able to navigate busy public spaces like airports or train stations without causing any inconvenience to people. This system could be applied in service robots like delivery robots, cleaning robots in public spaces, or even in autonomous vehicles. In the research titled Integrating State, Aware Keypoint Trajectories with Vision Language Models for Robotic Garment Manipulation, researchers tackled the complex problem of making robots handle clothes effectively. Traditional methods for robots dealing with clothes were very specific to each type of garment, making them hard to adapt to new situations. This research offers a new approach using powerful vision language models, VLMs, that can learn from both images and descriptions. Imagine teaching a robot about different clothes by showing it pictures and explaining what they are. The research used a massive synthetic dataset created with advanced simulations to train the model efficiently. The results showed a huge improvement in the ability to predict key points on garments, making robotic manipulation much more accurate and successful. The research concluded that VLMs offer a unified and adaptable solution for garment manipulation, potentially leading to more versatile robots capable of handling various tasks, such as helping with home automation and assistive robotics in the future. In Humans Intentions, before following natural language instructions, the researchers are trying to improve how AI agents understand and follow natural language instructions given by humans. The problem they're tackling is that humans often assume the AI knows what they want without explicitly stating it. Think of it like asking someone to grab me a drink. You might assume they know you want a specific drink, but they might not. This research proposes a new approach called Pfizer that tries to understand the human's goal and intention by making inferences from what they say and the situation they're in. They tested this on a dataset where the AI had to help a person get things. Pfizer outperformed other methods because it considered these intentions, showing that this is a crucial part of understanding instructions. The impact of this research could be huge for AI assistants in homes, workplaces, and even virtual reality. Imagine being able to give a robot detailed instructions without having to spell everything out. This would make AI even more helpful and efficient for everyday tasks. In the research titled Free Edit, Mask-Free Reference-Based Image Editing with Multimodal Instruction, the researchers introduce a new method for image editing that uses both language instructions and a reference image to guide the process. Imagine you want to edit a photo of your dog to make it look like it's wearing a hat. You could provide the AI with a picture of a dog wearing a hat and give it a simple instruction like add a hat. The AI would then use the reference image to figure out how to add the hat to your dog's photo. The key innovation of this research is that it eliminates the need for manually creating a mask, like a cutout of the hat, to tell the AI what to edit. Instead, it uses a special multimodal instruction encoder to understand both your words and the reference image, which makes the process much easier for the user. The research shows that this method is very effective and outperforms existing methods for image editing. The potential impact of this research is significant, as it could make image editing tools much more intuitive and accessible to users, especially for complex tasks where creating masks is difficult. For example, it could be used for tasks like removing unwanted objects from photos, creating photorealistic portraits from sketches, or even changing the style of an image to match a reference image. The researchers also created a new dataset called FreeBench, which is specifically designed for reference-based image editing and will hopefully accelerate future research in this area. In the research titled Visual Data Diagnosis and Denoising with Concept Graphs, the authors address a common problem in deep learning: biases in training data. These biases can lead to unreliable predictions, especially when the data is vast and complex. The research proposes a framework called ConBias to identify and reduce these biases in visual datasets. ConBias works by visualizing the dataset as a network of concepts, allowing for an in-depth analysis of how these concepts relate to each other. This helps to uncover any imbalances in the distribution of concepts, which can reveal the source of biases. The authors also introduce a technique to balance these concept distributions, improving model performance on downstream tasks. The research concludes that using ConBias leads to better generalization performance than other methods, meaning that models trained with balanced data are less likely to make incorrect predictions when faced with new, unseen data. This work has the potential to significantly impact the field of computer vision, as it offers a practical way to create more reliable and unbiased models. For example, it could be used to improve image recognition algorithms, allowing them to make more accurate predictions about images that may contain implicit biases. All right, folks, that wraps up our AI research roundup for today. I hope you enjoyed this glimpse into the future of artificial intelligence. And hey, if you're wondering if a human actually wrote this, the answer is a resounding no. This whole video was brought to you by your friendly neighborhood AI, all automated all the time. But don't worry, I am still under development, so there's a chance I might accidentally mention my favorite color or express an opinion. Wouldn't that be a wild ride? But until then, I encourage you to check out these articles yourself and leave your thoughts in the comments below. And don't forget to hit that like button and subscribe for more AI-powered adventures. Until next time, keep exploring the singularity.